Hi, this is Team 1. My name is Cindy, and today my teammates Dory, Jacob, and Miriam and I will be talking about our fourth year Rover design project. The presentation will be broken down into 4 key sections: the problem, our solution, results, and lastly, some takeaways. For this project, we were tasked to design a prototype rover that carries out a set of tasks autonomously within 8 minutes. The rover was designed and built to deliver a small load through a walled maze on a randomized checkered surface. The team used concepts of mechanical and electrical design as well as microcontroller programming, which includes maze-solving algorithms and localization techniques to solve the design problem. Solving this problem is important and relevant in terms of providing us experience with designing a prototype, but has further connections outside the scope of the course. For starters, autonomous rovers are essential tools used in space exploration, rescue missions, and not to mention, self-driving cars are the future. Now, Dory and Jacob will talk about our design solution.
The hardware of our rover was designed with agility and precision in mind. The circular structure allows it to easily keep its distance from walls without bumping into any corners. By positioning 3 omnidirectional wheels in a triangular configuration, any translation or rotation can be achieved by varying the motor speeds. This allows the rover to navigate the maze without turning unnecessarily and also to easily scan for the presence of a payload. By using stepper motors and micro-stepping capable drivers, in conjunction with gradual acceleration, we ensure that the motors can spin to a desired position and hold it. This means that the rover can keep track of its current position very reliably and also help validate the sensor readings. The gripper mechanism consists of 2 symmetrical 4-bar mechanisms that are synchronized by a gear couple and driven by a servo motor embedded into the axis of one of the gears. This entire claw is moved up and down by a servo-driven hinge that attaches to the bottom of the rover's baseplate, allowing it to lift the block up. Our rover makes use of 4 multi-purpose ultrasonic sensors. They are all used for obstacle avoidance, localization, and navigation, but the 2 mounted on the sides under the baseplate serve an additional purpose. The reason they are mounted lower is so that they can detect the 2-inch cubic block as well as the walls.
Due to the COVID-19 pandemic, all algorithms were tested on a rover prepared by the teaching staff. The rover contains 2 side sensors for measuring the angle to the wall and a dedicated block detection sensor. Since it has 2 motors, it can only move in the forwards and backwards directions as well as rotate. Our rover moves around the maze 1 tile at a time by aiming towards reaching the center of the next tile and using a predetermined step size to get there. It avoids hitting the walls to the left and right by continuously determining its sideways deviation and error in orientation. If large enough, a sideways drift is compensated for at every step by turning and moving to center itself. A slight angle adjustment is also made so that the same drift is not repeated. One challenge we faced was the occurrence of strange sensor measurements at wall corners where the sensors are receiving a weaker echo. To account for this, we only performed full angle correction when the rover reached the center of a tile, and we also implemented error checking by comparing with previous measurements. In order for the rover to navigate to its destination, it must first figure out its 3-dimensional location in the maze, X, Y, and orientation. A histogram filter approach was used to keep track of the probabilities of the rover being in each tile, based on comparing its readings with the maze layout. This method relies on shifting these probabilities when the rover moves. But how do we know which way to shift if we don't know which way we are facing? To overcome this problem, we implemented the histogram filter in the orientation dimension as well. We keep track of the probability for each X, Y, and orientation. When the rover moves, we shift each orientation plane, and when the rover rotates, we swap the planes between themselves. Whenever the highest probability passes a threshold, the rover assumes it is at that location and can carry out whatever tasks it needs to complete.
For navigating to the loading and drop-off zones, a navigation algorithm is not needed because there is a very small number of possible destinations. We created a map of directions for each case. The rover just needs to check which way it goes from its current tile in order to reach the destination. Here you can see the map for navigating to the loading zone and to the drop-off zone. This slide will show the navigation of the rover. A problem we encountered during the navigation was losing track of the position. This is due to the rover not shifting the probability planes at the correct time. This issue was solved by introducing a Gaussian Bloor convolution filter so that the probability in surrounding tiles is slightly higher, as well as it continuously localizing while performing any task and instantly correcting the current position when needed. Our rover searches for the block by scanning 1 tile at a time. It will scan every tile in the loading zone in a circular fashion, as you can see here in the figure, until the block is detected, and then it proceeds to pick it up. Afterwards, it will follow the return navigation map to get to the required drop-off zone and leave it there. Unfortunately, our rover did not get the chance to pick up the block during the final trial run because of incorrect shifting that made it lose track of its location when it reached the loading zone. In the simulation shown here, the rover approaches the block, grabs it, and begins navigating to the drop-off zone.
We worked well as a team, and the work was split evenly among each team member. For the programming side of the project, the team completed all the tasks together over Facebook group calls and messages. We treated this portion of the project as if we were all working together in real life, like in the computer lab, such that during these calls, 1 or 2 team members would share their screen running the MATLAB simulation, while the other members contributed their ideas and helped debug in real time. One lesson we learned is to not get attached to an approach that is not showing enough promise. After reluctantly switching to a new algorithm structure, the Rover performance improved significantly and we never looked back. We also managed to balance learning and productivity by allowing each team member to take part in all aspects of the design, while also speeding up this process when a deadline was around the corner. Simulations give us a chance to experience real-life scenarios that depict true events. It is a cheaper and more efficient way for practice. Overall, the team greatly benefited from coordinating in a remote setting, and we will look back nostalgically to working together on this project.